is 10 a.m.
Il y a
in
un endroit
Washington,
là, tu dois
D.C.,
dire partager
7 a.m.
son
in
ordinateur.
Silicon Valley,
Je sais
it
pas où
is
c'est.
4 p.m. in
Ouais.
Europe, and 3 p.m. in the beautiful
Thanks.
United
Ouais.
Kingdom with my colleague Helena Diaz is at the moment. Welcome to the Optica online industry meeting on quantum key distribution.
Hello again, we are back. I have been attending many conferences lately and I have witnessed the evolution of quantum technologies. It was great to be at the Quantum Flagship Pavilion at the Mobile World Congress, or to see the real-life demo at OFCNet by our corporate member QNect, and even to witness the advances on quantum communications at the Inside Quantum Technologies Conference in The Hague. All that in 3 weeks, which is very good for my frequent flyer miles. However, there is something I missed. If we are to be successful in quantum communications, we need the input of the telecom operators. So be prepared for this on 28th March. And for the first time on an Optica Online industry meeting, we collect the views of quantum key distribution from Verizon, British Telecom, Deutsche Telekom, ADVA, Huawei, and Airbus. What questions would you ask them? I have a few myself. How do they see the transition between QKD and post-QKD, what we call PQC, which is basically adding QKD cryptography to current infrastructures? Second, how are the current testbeds a solution for them to increase the TRL of the current QKD technologies? Third, when? When will we have QKD in our communications? And mainly, how will it affect us as their customers? And in the audience, and sharing one slide about how they can address the dreams and needs of those telecom operators we have. QSide, Lux Quanta, Quantelar, WeLink, KeyQuant, QNect, Think Quantum, and Quantum Dice. How do the unique selling points of these companies address the needs of the telecom operators? 2 hours, 6 telecom companies presenting what they need, and 8 success stories presenting what they have. Are you going to miss it? Register here to participate in the discussion in our Zoom channel, the QKD online event of the year. See you on Tuesday, 28 March at 7 a.m. Silicon Valley, 10 a.m. New York City, 3 p.m. in London, 4 p.m. in the Netherlands, 11 p.m. in Tokyo. Optica goes global.
Thank you very much, all of you, for being here with me. It is fantastic to see the community. Thank you, not only the telecom operators, but also our members. And I have to tell you, we're going to travel a lot to visit many quantum activities worldwide. My next one is called Gotham Q. Gotham Q. But you're going to hear a little bit more from that later on when Noel Goddard, the CEO of QNect, tells you about Gotham Q. Any Batman fans in the room? Let's start the meeting. I would like to let you know that this meeting is for 2 hours for all of you to get to know each other. So I'm going to start. My name is Jose Pozo, and I'm the Chief Technology Officer of Optica. Optica is many things, but on many things, it's also a global industry platform, a global industry association. I'm here with a team of experts on optics, on photonics, on interactive photonics, on laser, to connect our members with the end users. We have a team. Today, you're going to meet Pamela Robertson, our Deputy Senior Director on Business Development, and Helena Diaz, our Technical Director of Laser and Medical Technologies. We are a team of people that are led by industry. I would like to acknowledge our President, Michal Lipson, and also here our Corporate Engagement Council, full of people who tell us what to do. These are really our bosses. So if we don't do the things that you need, it's their fault. Blame them. Thank you so much, our Corporate Engagement Council, for all the amazing work that they are doing for us. Today is our 3rd event on the online industry meeting series, Quantum Key Distribution. Next week, always the last Tuesday of every month, we have an online industry meeting. Next one is hyperspectral imaging. We are addressing the needs of the agriculture and the needs on the process monitoring. It's going to be spectacular. Write it in your calendar and let you know that we organize many other different types of events, industry tutorials, product releases, industry summits, and user workshops. Make sure that you write them all in your calendar, optica.org/industry events. But today is all about QKD. And when it comes to QKD, we had a fantastic agenda of speakers. You saw the video, but what is even more important, we have been working very hard on connecting our members with the QKD activities. These are the companies here who registered for the meeting today, and that has something to add. This slide will be shared with all of you, with our corporate members, to make sure that we find ways to contact each other. At the end of the day, this meeting is a way to connect all of you. And also let you know that optica.org/market reports is a website that you should always keep in favorites. All of you corporate members, you can go there, download all the market reports that we have, select what you want, put your email, they come to your mailbox. You don't need to remember any password whatsoever. And the last thing I want to say is that this meeting is live streaming YouTube. So YouTubers of the world, if you have any questions for the speakers, write them in the chat and we'll read them. But this is also valid for people in the Zoom room. This is a very interactive event. This is a very interactive event. So you have any questions or suggestions, just make sure that you put them in the chat, or you raise your hand, or you simply unmute your phone and start speaking. I would like to give the floor and the attention of everyone to my very good colleague and dearest friend, Dr. Helena Diaz. Dr. Diaz, thank you very much for being with us all the way from Manchester, United Kingdom. The floor and the attention of the QKD community worldwide is yours.
Thank you so much, Jose. Thank you for that introduction. Good morning, everybody in Americas. Good afternoon in Europe and Africa, and good night in Asia and the other east of the world. So welcome all to the Quantum Communication meeting. My name is Elena Diaz-Riega, and I am the Technical Director in Optica, and I'm going to host you today. Thank you so much for being here. Thank you for the amazing speakers that we have. Thank you for everybody in the floor. This is going to be really, really good. Just to remind you, this is not going to be a webinar. This is a meeting. So please turn on your camera, put your name on it. Feel free to participate, to comment, to ask, to propose any solution. Use the chat and use the QA button for interact with all of us. Okay, everybody knows that quantum communication is an emerging field that is revolutionizing everything. It's going to be faster, it's going to be more secure, but there are so many challenges in quantum decoherence, in limited range, in complex implementation, security as user, and high cost. So to continue with this, hosting with me is my colleague Pamela Robertson, who is our senior director and is the newest acquisition in the industry team. Pamela.
Thank you, Helena. It's so nice to see you all. Thank you for the introduction. Yes, my name is Pamela Robertson, Senior Director of Business Development. Pleasure to be here. And I want to thank all of our speakers and for all of our attendees for being here today. I appreciate it. Everybody's in different time zones and locations, so thank you. I'd also like to introduce another quantum expert joining us today. He's going to help answer questions, look at ideas, and help us, facilitate conversations. I'd like to introduce Carl Williams. He's with NIST, is also just a great expert here at Optica. So thank you, Carl, for being here. Nice to see you today.
Thank you.
Nice to see you. Okay, Helena and team, let's get this started. We're going to start out today with our first speaker. Today we have Andrew Lloyd. Thank you, Andrew. He's Senior Manager of Optical Research and Distinguished Engineer at British Telecom, as well as a project manager for the EU Metro Hall project and the UK-funded Air QKD projects. He's also a key player at our executive forum at OFC in San Diego, my apologies. So he's also a key player on that and just joined us last month. And he's now joining us from Colchester in the UK. So welcome, Andrew. I will pass it over to you.
Yeah, hi, can you hear me?
Yes.
Great. Yeah, if you can see behind me, I'm in England with rain streaming down the window. So if I get distracted, it's wonderful, glorious British weather. I've got 6 minutes to talk about what's been happening in BT on quantum over the last 8 to 10 years. And you can see from the slide there that probably longer ago than that, top right, we launched some very early patents in the area, but they were way too long ago for them to be relevant now, 1992, 93. So we've been in this game a long time.
Andrew, am I the only one that doesn't see slides, or?
They're in non-presentation mode, is what I see.
Yeah, if you could just do a full screen presentation.
I had already, actually.
Sorry, Andrew. Sorry to interrupt. I just want to
no problem. Any
Yeah.
better?
So
No worries.
it's-
This is good. This is just like in live
Presentation
stream.
mode at my end.
Right. Hold on, we'll just get some help here. So yeah, this is just like when we're in the audience and there's someone at the podium and then someone in IT has to come and help out, right? We all know that feeling.
I think a quantum computer could solve this problem, but they're not big enough yet. So,
Matt, I think you're right. I think this whole team here can help us do this.
I'm just relaunching my PowerPoint. So if that was a problem, let me just relaunch it from scratch. Because I got a couple of messages from Zoom saying Zoom has just crashed.
oh,
That maybe that was part of the problem. Let's try again.
Okay.
at least we have the
Yeah, I'm pulling up. I could share your slides while we're.
yeah.
Let me try one more time first. Tell me if you can see this.
Yeah.
Now we can see it. Yes.
Just
And is it in full screen?
Perfect.
beautiful,
Yeah.
beautiful.
Let's try again.
I love the colors.
So look, we've been at this for a long time, since 1992, but actually seriously since probably 2013. And there's a whole load of information here about the kind of things we've been doing. You can see there I've been explaining quantum physics to Princess Anne in the UK. So if you have any questions, go and ask her, because I'm sure she understood every single bit of it. We've built a lot of trials with most of the vendors around the globe, including ID Quantique. And Toshiba, obviously, as well as working within the UK research community. We've built lots of trials and all of that kind of thing, as well as working with the standardization efforts and probably the kind of things that operators should be doing, like overall systems integration, etc. But what I want to really talk about now is a major trial that we launched in London about a year ago, 11 months ago, and I just want to report on how that's been going and how it works. So this is really not an experiment. It's a commercially ready trial to sell QKD to customers. It's a network, and what that means is it's more than 2 nodes. So in this case, 3 nodes. You can see where they are in London, 2 in central London, 1 in Slough, and that's near the a big data center district within the UK, because clearly I think one of the big use cases is secure comms into the data center. But what's the motivation behind it? The motivation isn't to test whether QKD works. We know that. Part of it is to see how it would work in a network context when I want to put multiple customers, hopefully dozens of customers, onto the same quantum infrastructure. How would we do that? Because then there's other questions around not just the raw technology, but the overall management of it, making sure the keys go the right way. How do you build an access and then a core, then another access bit? And how does that all kind of stitch together? What I don't think you want to do ever in a network is just connect pairs of people together or pairs of companies together without sharing infrastructure. You have to share in order to get the kind of cost benefits. And so that's one of the main purposes of the trial. The other one is, what are the use cases? So what are customers actually going to want to use this for? So just one very short slide on the technical complexities of this. And it keeps going forward. I don't know why that keeps going forward. You can see on this slide, at the bottom, we've got the QKD links. But actually, there's an awful lot of the design here that's nothing to do with quantum. And it's basically integration of quantum into the rest of the network. So the green there is classic WDM. It's taking unencrypted Ethernet from customers, encrypting it with QKD keys, and then transporting that WDM across a network at the same time as carrying the keys that have encrypted that data across the same network. And then you see there this KMS, which is a ubiquitous management service across the whole network, making sure the keys are in the right place at the right time stamped, being passed on to the edge of the network where they can be decrypted. So the principle behind this whole thing is you encrypt the data at the ingress at the customer site, and then you don't touch it again. You don't decrypt until the far end. Okay, so you try and keep it as safe as possible. And then all that kind of internal Metro core quantum is doing, it's just getting keys from one end to the other. That's all it's doing, essentially. And then the data is going its own sweet way, a completely different path, potentially, or it could share fiber. It doesn't have to. But the job of the quantum metro network is just to get those edge keys from one end to the other. Now, this is part of a big kind of strategy for us, and that is to go from, we're at point 2 at the moment, so to go from basic customer point-to-point links to metro links, within a couple of years to bring the global key distribution problem to commercial reality with satellite QKD. I think that's about 2 years away. Then ultimately then to start to roll out a national quantum service in the UK and around the planet. I think this is completely realistic within 3 to 4 years. I don't think any more kind of technology development or science is needed to do this. It's really just a question of how those customers start to engage. And the real challenge, and something we can talk about, I think, in this conversation in the next 2 hours, is what will customers use this for? What is the level of the appetite there? It's still not really enough. And it needs to grow to a point where, you know, we have potentially dozens of QKD vendors all pitching in with cost-effective technology that we can build. Thank you very much.
You're on mute, Helena.
Thank you. Thank you so much, Andrew. I mean, I'm really amazed that you are talking about 3 to 4 years to be a full network working. So it's really impressive. So we have any questions, any comments that we have here? Please, people, feel free to put your questions and your comments. We'll be open the mic for you. Okay. Yeah. So we have people from everywhere. We have hello Florian. We have Amara Loli, Robertson Oliveira, Goodness Endulver. Okay, Mukul. Thank you so much for being here. So can you tell us a little bit more, like how it's going to be the implementation for this? I mean, I'm really curious. I mean, because for UK, I can understand it could be not that big of the area. So how is it going to expand to the war?
I think there's different ways of doing this. You can think about the core network first, and for that you need a very specific QKD core technology, and you probably only need to connect 10 to 15 major nodes in the UK, and that would include obviously Wales and England and Ireland and Scotland. The distances are several hundred kilometers, but that's okay. You can build trusted nodes to do that. And then so once you've built that infrastructure, it's probably not a lot of QKD. It's probably tens of boxes, probably costing a few million. It's not, you know, it's not massive. And then you get national connectivity. And then I think once you've done that, within 2 to 3 years, you'll have a satellite capability coming in to do the global piece. And then I think probably the real cost challenge is going to be in the access, because installing QKD to an SME down the road from me, that's a really expensive thing to do. And maybe there we need to think and be more challenged in how do we do secure solutions at the edge of the network.
Yeah, that's a total challenge. I mean, really, this is, but I can see it coming. So thank you so much. We have Vanessa Diaz from Lux Quanta. Vanessa, are you? Can you turn on your mic and ask yourself?
Yes. Hi, hello everybody. Well, already Andrew answered the question. Hi, Andrew. It's nice seeing you again. Because you were talking about 10 boxes roughly for the core, and then the challenging part will be for the access. Have you sized what would be the number of devices that will be needed for the access roughly?
Well, the access devices, it's one per customer, literally. So, you know, I don't think we're not talking millions of domestic customers, clearly. I think we're talking about, nevertheless, thousands of business customers. And the question is that actually feasible to give QKD on a dedicated fiber to a business customer, you know, in the industry, or should we find a more cost-effective way of doing that edge connectivity, for example, using PQC? Or maybe it's a mixture of both. And I can imagine a customer that's going into a data center where this, you know, the data center is housing multiple customers. So in that case, maybe full QKD makes sense, or maybe it's a business park. But if it's just a single customer on a high street or something, maybe it's too much to expect, you know, a full-blown QKD link there, and maybe something more prosaic like a PQC would be a good solution.
Thanks. And when you talk about dedicated fiber, you're talking about a full fiber, you mean, like not a band or anything? You are talking about?
Well, if it's an access fiber going into a customer, they tend to just have one fiber, and it's not a fiber pair, it's just literally one fiber. So you need to find a way to put QKD plus the whatever Ethernet connectivity that customer wants, which could be 10, let's say 10 gig Ethernet, on that same single fiber. Now you might say that's really challenging, but actually the distance is not great. It's only like 5 or 10 kilometers. So it's not that you've got a big, technical challenge. It's just trying to make sure it all fits within the fiber. And clearly QKD will take one wavelength, the Ethernet will take another one. So you could put your QKD at 1.3 microns and your 10 gig Ethernet could be at 1.5, or you could swap them around.
Right.
Yeah.
Okay. Yes.
Yeah.
Absolutely.
Thank you. Vanessa, I know you have one slide that you can share with us, please.
Yeah, it comes very handy. So
yeah. So yeah. And Ahmed, I got you on my list that you are coming after Vanessa presents. Okay. Yeah. Thank you.
Perfecto. Okay. Well, Andrew, it comes very handy for distribution called continuous one. And that
is it okay for
makes
everybody?
the system
okay.
was released literally a few weeks.
I think we are losing you, Vanessa. Hello? Yeah?
Yeah, I think we probably lost.
We lost Vanessa. Okay, Vanessa, we try to.
Oh, there she is.
You coming back? Okay.
Yeah, I don't know what happened there. So did you manage to see the slide that I was sharing?
Not really. Yeah.
What about now?
Now it is there. Yeah. So yeah, we lost you for a little while. Yeah.
Right. So what I was saying, very much in line with Andrew was talking about, no? So that co-propagation in the same optical fiber. So Lux Quanta works, delivers this other flavor of quantum key distribution called continuous variable. So it's based on Bohrian detection, and that because of the characteristics of the link delivers that fantastic co-propagation capabilities that you need. So we were releasing this system literally a few weeks ago. So you could tune that quantum channel in the C-band wherever you need it. And so it delivers very great DWDM coexistence, alongside any other wavelength schemes that you need to work with in the access. The system is fully automated, real-time error correction implemented as well, state-of-the-art, delivering extremely high performances here, and also in terms of digital signal processing. The interfaces standardized ETSI, although we can work with any other interface that you need, we can work on that too. And then the distances, we always talk about this power budget, the 8 dBs, depending on what type of fiber link you deliver, we'll be able to meet this target around 40 kilometers or less. But that should be enough for what you're describing. So I'm pretty sure that the flavor of this technology, continuous variable, could solve this challenge in the access.
The killer question, Vanessa, of course, is for CV. Do you see a big cost benefit as well compared to DV?
Yes, that's a challenge. That's what we want to do with the technology. So we have to be more competitive in price. We want to do that. And there is this work in parallel that is running, integrating the solution into photonic in a photonic chip. That's what's going to make us very competitive in a few years down the line in terms of price. So this technology is very disruptive precisely for that reason, because the pathway towards scalability in terms of integration, photonic integration, is very clear. There is nothing weird in our system that cannot be put on a photonic chip. So that's the
I think you guys definitely need to talk each other. So we put you in contact. That's really good. Thank you so much. We have Ahmad Vadiet for OptiWare. So he raised his hand. So Ahmad, tell us.
Yes, thanks, Andrew, for the presentation. Actually, my question is kind of answered semi by Vanessa, because I was asking about the WDM application for a quantum key distribution. Andrew, you mentioned that you're gonna send a key per user. Are you gonna, let's say, send it per wavelength as well, or how it's gonna be done on the fiber?
In the access, you have one fiber, so everything has to go on that. So your keys are dedicated to that access link, as well as the Ethernet. In the core network, the keys can be shared. So you can build a completely separate QKD network that doesn't have data on the same fiber. It doesn't have to have coexistence. You can send your data a completely different route on different fibers, and you can dedicate your core network. You can choose a fiber and dedicate it to QKD, which means you can generate much, much higher key rates and share those keys to multiple, hopefully thousands of customers.
Perfect. Thanks.
Yeah. So we have another question that is coming for Gunnar Sekar, Cisco. Gunnar, could you please turn on your mic and ask yourself?
Andrew. Yeah. Good question. So is the key specific to a fiber, or is it specific to a wavelength or a channel on fiber?
I would very much rushed that slide, so apologies. So you started an access link and you generate a specific key for your customer. Then in the core, that key is then being shared with multiple other customers, hopefully thousands of customers all coming in to the same point. And those keys are then aggregated and carried on a separate QKD system that is just there to carry keys using an exclusive or some kind of function to the far end where again, that key is separated and sent to the customer. So the access bits, the keys are dedicated to a specific customer. In the core, the QKD is carrying QKD. So it's QKD carrying QKD.
Yeah. Excellent. So we also have Jean-Sébastien Pegon from ID Quantique. He wants to ask to Vanessa. So Jan, can you please turn on your mic?
Yes, thank you. So the question is, do you see a limitation in the number of classical channels that can be sent in the same fiber when doing WDM as a quantum channel?
No, that's for me, no, there should be no limitation. We have to be careful with Raman, of course, because it can affect the characteristics of the quantum channel. But apart from that, we will work with a standard layout, whether it's DWDM or CWDM or any PON.
Yeah. And
Okay.
Thank you so much. Thank you
Thank
so much,
you.
Vanessa, for answering that. The very last question for this, so we can move forward, is Robert Keys from Siena. Robert, can you please tell yourself your question?
Yeah, it was just a question to Andrew. When you say a single fiber to the access user, do you mean truly a single fiber or a single fiber pair? So does it need to be a bi-directional solution?
Robert, how come we didn't meet at OFC? I saw you, but we never got to talk.
Great.
And then to answer the question, if we could have a single fiber, literally one fiber, that would be incredibly useful, because often with customers we just have a single fiber. That's all we really want to do is manage one fiber, because it's really hard managing two. So if you can find a way of doing a QKD plus Ethernet on a single fiber, that would be quite amazing, I think.
So you just took a challenge and made it more difficult, but that's okay. I like a challenge.
Yeah, but the distances are short.
Yeah. And there's no amplifiers involved.
Exactly.
Yes.
We should meet sometime, Andrea. We'll see if I can come and visit you.
Sounds great.
Okay, so thank you so much, Andrew. I mean, really, this is a great start. So, and this is really good. This is what we do. We put the people to meet each other. You see, it's working. It's really good. I'm very happy. That makes me really happy. So we are going to have our next speaker. Pamela, do you want to introduce it, please? Okay, I will do it then. Okay, so our next speaker, okay, is Max Sterlington. He's coming all the way from Texas, so it's not like here that is rainy. Over there is really sunny and nice. Matt is an engineer at Verizon. Okay, so basically is telecommunication technologies, leading the LT routers and Ethernet roadmaps on it. So let's hear what Matt Sterlington have to tell us about quantum networking. Matt, all yours.
Can you hear me? And
yeah, very good.
Is my slides okay? Or is it? Can you see the slides?
We can see the slides, but you need
yeah, maybe put it in presentation mode, Matt.
Yeah, I had two monitors and
it is in presentation mode. It's like you got to flip it to
switch.
Let me reshare. Hold on.
And
thank you so much. Yeah.
And thank you, Helena. Remember, we were switching. We're going back and forth.
Yeah.
I don't know why it still thinks I have 2 monitors.
That's okay. I think go ahead.
Sure. Can I go ahead?
Yeah, go ahead.
Okay, so I'm Matt Sterlington. I'm an associate fellow in the Verizon technology labs. And what we do is we investigate new technologies to use across our networks, whether it's wireless or wireline. And so I'm kind of stuck with quantum, and I see that as a good thing because you know, the tail is 10 or 15 years out maybe for some things. So that's job security. But so a quick, for people that don't know, Verizon is a big carrier in the United States. And really what I want to focus on this slide is the bottom right, where it says we have over 1 million miles of global fiber, and most of that is in the United States. And that's only going to increase as we go to 5G and maybe to 6G. You know, you have all this proliferation of cell towers, and you have to run fiber to them. So we have this, we've always had, but we have a bigger infrastructure of fiber in the United States, which carries everything, you know, imaginable, and possibly in the future, quantum networking. So what I'm going to talk about is more from a provider point of view, what a quantum network would look like. So just like with everybody else, you know, like BT, we're investigating these new technologies, and QKD is one of them. But if you look beyond that, there might be some quantum networking coming. So we're collaborating, since we're not quantum physicists, we're not scientists, we're network builders. So we collaborate with partners like in QEDC, QNext, Chicago Quantum Exchange, which are consortia. We collaborate with them to learn about the technology and also to get in at the beginning so we can talk with the vendors and say, yeah, we're a telco and we have certain expectations of what networks will look like, what equipment will look like. So we start the conversation early, and you know, we kind of share ideas. So what I will say is we've done several trials on post-quantum cryptography and QKD, and I put some QR codes in there. So if you're watching this on video or you're watching now, you can go right to the press releases. And if you have any questions directly about the trials, I can answer that. But what I'm saying is we have this fiber backbone across the United States. If you want to go from New York to LA, that's a long run. And at some point, maybe we'll need a quantum network that goes across the country. And you'll need a good fiber backbone to do that. And that's what we're looking to do and to prepare for. So what will a quantum network look like? And this could be QKD, this could be computing or distributed computing between 2 quantum computers. What's it going to look like? And I'm a network guy, so to me, the quantum network will look, you know, essentially the same as our classical network. You'll have communities of interest. Maybe in New York City, you'll have a metro with dense fiber, with some long haul fiber, maybe to Boston. And, you know, you have customers in Boston and New York. Maybe they need that connection. However, there's a limitation on quantum transmission that maybe you can only go so far, and we need to figure out how far we can go. But at some point, to go from New York to LA, you're going to need some type of device, and we'll call that a quantum repeater. And that's kind of where we're plugged into these academic universities and startup vendors to look at where the technology can go to enable these quantum repeaters, so we can go more than 100 kilometers. So just like today, you know, as we started, we built transmission networks and we layered on top of them data networks, switching networks. At some point, this quantum network will increase in size, and you'll need some kind of routing and switching of these qubits or quantum signals. And that's going to require a lot of standards work, and it's going to require a lot of equipment vendors to do some research. And then, like Andrew said, the best possibility is if we can coexist quantum networks and classical networks, or the signals onto the same facilities and fibers. Just because if you look at a fiber as a subdivision of houses, you have maybe 100 channels where you could send 400 gig of data. Well, we would like to put quantum in there as maybe one of those channels. I know I'm not a physicist, so I hear it's difficult, but I'm telling you, what a telco provider would prefer is to have a integration of quantum and classical on the same fiber. So, what do we want from network equipment? And this includes any network equipment and specifically QKD and quantum equipment. Anything in the United States, and I'm sure the UK has standards as well, the equipment coming in has to meet space, power, heat dissipation requirements, because I can't have a quantum repeater in a rack overheat and then bring down, the internet backbone, for example. So in these COs, so that's a clean looking CO. However, you can see how much equipment is in there. And if the chillers were to fail, the temperature will go up. So you need to be able to compensate for temperature swings, and that's probably pretty difficult for quantum signals. So in the United States, we have this thing called NEBS. Vendors really hate it, but that's what we require before we can let anything into our central offices or network. Now we move to this equipment is going to be writing field fiber, optical field fiber, standard fiber that we have all across the United States. It would be great if it could transmit in the C or the L band where we have our transmission signals now. I know some QKD devices, operate in 1310. We could possibly do that. It might add another splitter and add some loss, but that's something we can look at. But we really do want them to coexist on the same fiber as classical signals. Now, I'm not very familiar with fiber deployments in other countries, but in the United States, you're going to have a mix of buried and aerial fiber. So you're going to have wooden poles, like a lot in the Northeast. You'll have wooden poles carrying fibers, swinging in the wind, wild temperature changes, snow on them. And then you're going to have buried fibers going through Manhattan, and the manholes will fill with water. So things like that could change the environmentals of the transmission over the fiber. And we know how to compensate for that on 100G or 400G signals. What do we need to do with quantum signals? Now, just like with traditional transmission, we have EDFAs or amplifiers, let's say every 80 kilometers. So you can go from New York to LA. Well, like I said, we're going to need quantum repeaters to go that same distance. But wouldn't it be great if we could coincide the quantum repeater and the EDFA in the same hut or shelter, so that we don't have to stagger them? So, for example, if a quantum technology says you have to have repeaters every 10 kilometers, well, that might hurt the business case. If you say it's every 80 kilometers, well, that's a little more palatable. But what I think is the most important is, if you think about it, these telco networks, BT or Verizon, over the decades, they work really well, whether it's transmission or data. And a lot of that has to do with the legwork in making these networks manageable, alarmable. You can surveil them. You can monitor the performance and maybe get ahead of problems. So as we move to quantum networking, we're going to have to focus and say, what are the metrics we need to measure to make sure this equipment is operating, or this data circuit, this quantum data circuit is operating well? What are those metrics we need in the quantum world versus the classical world? Because we have to have that ahead of time so we can deploy this and know it's operating well or it needs some adjustment. Oh, wrong way. So that's all I had as far as slides. And if you have any questions, I'm here. So thanks.
Thanks, Matt.
Thank you. Yeah,
Oh,
sorry,
sorry.
go.
Yeah, thanks, Matt. And I might have a hard time seeing if anybody has a hand up, if there's any questions, but please open your camera or turn on your camera or ask a question.
There are some questions. Yes. So talking about this, there is something that is what you are showing is the complexity of the implementation. And this is one of the biggest challenge. So there are so many things. So here in the room, we have Mirela Koleva. She says that for Quantopticon, sorry about that. So Mirela, do you want to open your mic?
Sure.
Yeah. Okay. So tell us a little bit that what you can offer to Matt.
Yeah, so our software is basically targeting discrete variable QKD. We're also actually modeling quantum memories, so we can help with that. I think we should probably set up a call and discuss in more detail.
Yeah, okay. Yeah, because we're familiar with attenuation, dispersion, higher order dispersion for classical signals. And like I said, we're not physicists, so I need to know ahead of time what I need to look for as far as how these signals operate over field fiber. So first of all, I need to know what to look for, and then we can say, well, these are the numbers we should hit, or what do we do if it's approaching this? So yeah, I think given the fact that quantum memories aren't pervasive in the marketplace, modeling will help out in the beginning.
Thank you, Matt. And thank you, Marla, for the question. Looks like we also have a question from Constantino. Would you like to ask your question?
Yes, hello, can you hear me?
Yes.
Yes.
Perfect. So yes, Matt, I wanted to ask why you mentioned repeatedly that you're waiting for quantum memories and quantum repeaters. And why aren't you considering, for example, satellites to serve a long haul, such as between New York and Los Angeles? That would make everything simpler. And that's the approach that Europe is following, and also the Chinese have followed for their continental scale quantum networks.
Yeah, and that's a good question. I mean, I'm speaking as a Verizon engineer, and we are a network provider, landline network provider in the United States. So could we consider satellite? Yeah. I mean, Verizon is a large company, and they probably have some time on transponders for something I don't know about, but it's not a big part of our business. And could it scale? So if you look at classical networks today, could you recreate what we do on a dense fiber network over satellite? That many 100G or 400G signals, could you do that over satellite? So yeah, I know I can go 2,000 kilometers with satellite, but as a business provider to enterprise customers in the United States, would satellite scale? And I'm not a business guy, I'm a network guy. So if it does scale, then Verizon would do it.
Nice. Hey, thanks, Matt. Actually, Constantino, this might be a perfect time for you to share your one slide. How does that work for you?
Yeah, sure. I'll try to get it going.
Okay, so this is our one slide from Think Quantum, so thank you.
Let me just go into presentation mode. It should be F5, right?
So I have been thinking about free space, just as a side. I see that on your slide.
Yes. Can you see it in full screen?
Yes.
Okay, so this is our one slide. We're Think Quantum. We are a spin-off of the University of Padova, but we also have some part from Officina Stellare, which is a premium provider of telescopes for satellite and ground stations. As being part of the University of Padova, we have a strong heritage in space-based quantum key distribution, and both in satellite links and also free space links. In fact, the two professors that co-founded Quantuma were the pioneers of satellite-based quantum communications, at least here in Europe. So I think Quantuma, we are a fully European company, and we have several solutions for the end users for QKD. So we provide QKD systems. These are our QKey line, but we also provide the quantum random number generators. So this is something that you also mentioned in your slide, Matt. Our QKD system, they work both in fiber systems and they also work for free space links, for example. And we sustain maximum losses of around 20 dB for our standard version and 23 dB for our premium version. So basically here we already are able to provide a distance that is compatible with what you called the jump between the classical repeaters. So what's different from our QKD system with respect to the other QKD systems? Well, first of all, inside our QKD system, we integrate a quantum random number generator, and all our key that we generate is basically derived from the quantum random number generator, giving it the absolutely sized level of security available. Then we only use a single fiber for everything. Basically, we do anything regarding synchronization and quantum key generation using a single fiber. And then we give the end user the flexibility to choose between any Ethernet protocol or whatever they want for the classical communications. And then regarding our quantum random number generator, we are able to deliver an internal quantum entropy of 2 gigabits per second. And then after post-processing, we're able to deliver 330 megabits per second to the end user. So basically, this is it. And also, I would like to stress that our solution is you can use it for fiber-based systems, but also for free space systems. We're using polarization encoding, which is optimal for also free space propagation. And in fact, Quantum is working quite a lot to make our QKey system not only available for ground, but also for satellite integrations.
Oh, that's fantastic. So Grace, you got to be able to present this to Verizon, British Telecom. You have been able to connect with these people, so that's great, Matt. I'm glad you got to see that. I guess I need more coffee. Thank you, Constantino. Why don't we, I know a couple of people have some questions here in the chat. Maybe if you can connect them there, because I do think we need to move on to our next speaker. But please connect in chat, and then we can also, go Helena.
Yeah, let's have just one more question, because we still have time for one question, but we are still all the questions that are going to be here, they are going to share with the speakers, and if you want to have any introduction, please let us know. That would be very, very pleasure to make the introduction. So we have Jason Palibar from Iridian. So Jason, if you can open pretty quick your mic. And we have talked. Okay.
We lose him.
Jason. Okay, Jason is not opening the mic, so I can read it for him. So Iridian Spectral Technologies is asking. So it says including polarization phase differences dichroic. So basically, is saying like there are some filters or QKD that they can be used. So let's move. We have a raised hand. Sorry, I couldn't see the name. Who is raising the hand? Okay. Oh, Taokif. Oh, hello. How you doing, Taokif? Hi.
Hi, how are you doing?
Hi, nice seeing you. Hello. Yeah, welcome. Yeah, please.
Hi, thank you. Yeah, it was just a very interesting talk. Thank you. You're talking of very, very long distances. I mean, from New York to Los Angeles, that's several thousand of kilometers. I think 4,000 or 5,000 of fibers that you want to put there to deploy. Yeah, for quantum communications, you know that propagation losses are very important in fibers, and in the standard fibers, it's about 0.2 dB per kilometers. Do you consider deploying ultra low loss fibers in your network?
That's an excellent question. Sorry, I didn't mean to cut you off.
Yeah, that's it. That's
okay. So Are we considering it? I would say it's something we would research now. So if you look at our fiber backbone, I'm not sure how many billions of dollars it took to cross the United States, and to replace that with ultra low loss fiber, and we might be driven to do that, but it would be a very high capital cost, to begin that process, and then therefore the economics of the revenue services you're going to offer over that fiber would have to be very tightly looked at. It would cost a lot of money to pull fiber across the United States and essentially kind of augment what we have there with new fiber. So, and again, I'm an engineer. I don't really mess with the spreadsheets, but I can tell you pulling a fiber from a street in Manhattan into a bank, for example, is a lot of money per 100 feet. And to do it nationwide would be pretty tough. And that's a good thing. You mentioned, New York to LA is long, but if we're going to offer a service, we want it to be kind of ubiquitous across our footprint. So we wouldn't necessarily want to offer a service, oh, this will work in New York City, and then, we can't really go outside of it. We'd want to plan, just like with 5G, we want to plan our build out so that it spreads quickly and goes across the nation. And it's a pretty big area-wise nation, and fiber losses. So we have lots of amplifier chains, and we would expect lots of quantum repeater chains. I'm not sure if I answered your question.
Yeah, you did. Thank you. Yeah, I could imagine it's really a matter of cost, and I wanted to understand if this was in the roadmap somewhere to do this sort of transition.
Yeah,
but,
and it might be. I don't deal with the optical fiber plant directly much, but I know I've heard some investigation of new fiber types. So
Thank you both. And if there's anybody else that needs any connections across this team, just let me know how we can help you, and love to help everybody get in contact with the right person that they need to talk to. So just to continue with this telecommunication providers, we're going to have our next speaker here. So Felix, welcome. We have Felix Wissel. He is the fixed.
Welcome, everyone.
No, you there?
Yeah, I'm here. Test.
Okay,
Can you hear
and
me?
I'll just, let me give you a little intro first. So
Perfect.
So he joined Deutsche Telekom in 2014. He's participated in several international projects for ESA and the EU. He's now heavily involved in quantum cryptography and works with deploying a QKD platform for Deutsche I do need more coffee. For Deutsche Telekom. He's a senior expert in networked concepts and architecture. So Felix, welcome. Thank you for joining us. And yes, we see your slides. Maybe if you can put in presentation mode.
I did. So which kind of screen are you seeing?
The
wrong one?
Well, just the not presentation, but we can see your slides.
Yeah, but the presentation mode or the
No, you don't have in presentation mode yet. Yeah, we can see it like you are working. So if you
too bad.
It's okay.
No, it's not okay. It's now better.
Nope.
There
now
you go.
It is.
Perfect. Okay.
Now it is great.
It is?
The floor is yours. Yes, please go ahead.
Okay. So first, thanks a lot for the invitation and the possibility to be here. Cool to have a couple of faces or names that I recognize from previous events, and a lot of new faces which soon hopefully will be familiar. So as introduced, thanks for the introduction, by the way, as well. I'm from DT. I will tell you about 2 recent projects and about what we did. During the talks that have already been given, I recognized that I should have taken my old slides that I presented last time, because a couple of questions that came up here are, how do I say, they better would have been covered by the old slides. But anyway, we can talk about these things, I don't know, over coffee. So that's just a short review of what Deutsche Telekom was doing, is currently doing, and plans to do in the next future. So we have a long-standing history, not quite as long as BT, but quite as long. We had a couple of research projects going on, mostly funded by the Commission, by European Commission, but also by the German Ministry for Education and Research. And I saw a couple of representatives of the QNet project also in the call. So that is the lowest one here. For those not of Europe, you are not familiar with OpenQKD, I guess, or with EuroQCI, but there's a big initiative in Europe, mostly triggered and driven by the European Commission to go for a European quantum communication infrastructure. And as preparation for that, we had these research projects. We also had some commercial studies, one feasibility study where we participated, and then a detailed design study, QSafe, Quantum Safe Architecture for Europe, where DT was prime. Currently, we have two major pillars what we are doing on QKD. One project is called DemoQuant, the other one is called Petrus, and for both of these slides we have for both of these projects I have two additional slides, so I will skip over them by now. I will only shortly mention other activities that we are doing. We are trying to combine QKD with machine learning. There's a German industry association on quantum security. A couple of people in the calls know that and are part of that. We have a research cooperation with our local university here, where we are actually going to deploy or to build our own quantum prototypes with a certain protocol. We are active in standardization. Colleagues of mine from the telecom security are working on protection profiles, which might also be relevant for you. I'm here representing the Deutsche Telekom engineering department, and we are planning for the future activities to be participating in the so-called framework partnership agreement. That's a follow-up that's a continuation of the quantum flagship. And what had been started in projects like Civic is now prolongated. Actually, it did already start, so it should have been moved. Where's my mouse? Well, okay, you can imagine, even though you cannot see my mouse, so the quantum secure network project should have been moved to present. Although we are preparing for an expected call from the Commission on testing and validation infrastructure. And the Quantum Coordination Board is also some kind of like aligning between all the different stakeholders that are floating around currently. And it's important to have an information flow going on. Okay, I will now, that is the general overview, and I will now talk explicitly about these two projects. So DemoQuant, that's the first one. It's funded by German Ministry for Education and Research. Total budget is about 50 million. About 2/3 of that is for Deutsche Telekom, but it's not all funding money. So we have to bring our own budget on the table, half of it. And what's the scope? We are going to deploy a large-scale network, or first we start with a single link from Berlin to Bonn, and that's shown here. For those of you not familiar with the German or with the European geography, so this is that's the northern part of Germany. So you can imagine the rest below, and we have France to the left, Poland to the right, Italy and Spain, Austria and Swiss and Italy to the south, and Denmark to the north. Our goal is to really do what has been discussed by Andrew and by Matt in the previous talks. We will prepare the deployment of a nationwide QKD network, and all the problems that we talked about already or that have been mentioned, the limited distance range, the necessity for kind of repeater stations, not necessarily quantum repeater, but could be a trusted node. The monitoring of all these equipment deployed in these things need to be covered. The integration in the real networks, the determination of key rates that are required. A big important point is the separation between the payload that is encrypted, for example, from the key path. Andrew mentioned that. So what we are trying to do is here to come up with a close to real network operation, and we are doing all the things that are necessary to come up with a real network. In the long run, we want to connect every possible location in Germany with quantum services. So that will not happen in one step, but we will grow. But at some point, it should be possible to have any-to-any connection. So it's like in the telephone system or like in the internet. If you know a phone number from someone, you can call him. And here as well, if you know the counterpart of your communication relationship, you can dial and say, okay, please provide a quantum key between these two locations. And then the platform that we're going to build provides these quantum secure keys. Our partners are ATWA, also here in the call, and I think I'm not totally wrong, Helmut will give a talk. We have Roland Schwarz for the security key quant, also represented here by Ulrich Eismann, sorry for that. And we have the two local universities from our hometown where we do the research and look at certain kind of things. So that's in total a quick overview of a DemoQuant. And here you can see what DemoQuant means. It's an acronym, and as usual in these research projects, it's a funny acronym covering what we're doing. Next big thing is Petrus. It's a new coordination support action for the so-called Digital Euro program. Digital Euro program is one of these pillars from the European Union to come up with EuroQCI. EuroQCI is the European Quantum Communication Infrastructure. All of these things have been funded by the Commission, and a lot of money is pumped in the market here. What we said is the following: there has been a certain history, and we took the primes of the most important projects and most important activities that took place. So we have AIT, the Austrian Institute of Technology, who were responsible for the OpenQKD project for the last 4 years, I guess. We have Airbus as representative, as prime of a study called COSAC, and Thales 6 from the French company on security. They were the prime for QCI for EU, so that was the first part of the feasibility study. And these feasibility studies have been extended to a detailed design. Again, there had been 2 studies in parallel, one by Airbus, one by DT, with our partners as well. Basically, the teams have been the same as before. And now we all joined up together and teamed up and joined our forces. And we said, okay, let's go for Petrus. Petrus started off as a nickname, but later on it turned out that Petrus is a guy in the Catholic Church who distributes keys, or who owns keys. So that was matching the situation. We are doing the coordination for all these different projects within the Digital Euro program. So we have a couple of member state projects that are responsible to deploy a national QCI in their member states. And we have a couple of projects that are working on industrialization and equipment manufacturer. Some of them have been in the call, like Vanessa already presented the Lux Quanta, but Ulrich, for example, Eismann from KeyQuant is the same. And I forgot someone, but that is the contact will be made by the organizers if there is need. So next slide shows, and I have 2 more slides and I'm done. This is a simplified functional architecture for a QKD network. Don't be misled by the overview, by the title here. We deployed this one. We drafted this architecture for EuroQCI in our own project, but it's so generic it could be adopted for every quantum internet and or quantum QKD distribution network. I guess BT follows the same approach. So on the lowest layer, we have the actual key generation, hop by hop, and we have these distance limitations. So we have a quantum key, for example, in red, and then we have a different link, a second hop producing a violet key, and then we have a final yellow key. So these are the several individual hops where quantum mechanics is used to produce a secure key. Then we have a key management forwarding layer where we use these keys to forward a random number. And this random number is then handed over at the 2 endpoints to the customers. And if you don't have only a single link as shown here, but if you have a meshed network, you can imagine that the same mechanism can be used to provide arbitrary to provide a random number to arbitrary endpoints. So the highest layer is the key consumption layer where the applications take place, like for example, an encryptor, or some applications don't need encryption. They only need a secure authentication depending on the use case. We don't care. Our platform is able to deliver keys to whomever who might need keys. And in between, of course, we have some kind of network and control layer, and we are going for a centralized software-defined networking approach to organize all that things that are shown here. And one of the cool things that is implicitly part of that network here is that you can easily exchange the technology without spoiling the whole architecture. So the upper part of the architecture are stable, even though we replace a terrestrial fiber-based link with a satellite link. And we can even go a step further by saying, well, at those part of the networks where we don't have secured enough locations, which are, well, for QKD, as a side remark, you need to have secured physically secured locations. Otherwise, an attacker would simply attack your devices, and that may not happen. So you need, countermeasures for that. But there are situations like antenna poles or customer locations which cannot be secured in the same required way. So for these situations, we simply use post-quantum algorithms to extend the QKD platform to these outer network areas. And in the same style, we also go for what we call hybrid approach that has also been mentioned before, that we don't rely on QKD alone. Every link that you see here is additionally secured by a post-quantum encryption scheme. Okay, that's my conclusion slide. So design guidelines for a national QCI or for any other QKD network. First, we strongly recommend a separation of the actual key distribution platform and the key consuming devices. If there is a differentiation, then it should not be happen on the level of use cases or on the level of applications. The only reason that I see the only reason I see which as a consequence will make it necessary, grammar might be wrong here, sorry for that, is when you go for different classification levels. So it might be that for applications which are top secret, you are not allowed to share the same infrastructure than for critical infrastructure alone, which is not classified. So that is the reason why we think of, okay, separation or segregation is necessary. But to differentiate for what such a quantum key is actually needed, or why is an application in need of a quantum key, that is a wrong question. It's similar like if you have a car, you do not differentiate in that you use a car to go to the groceries, or you have a car to bring the kids to school, or you have a car for sports, I don't know. The use case, the prime use case of a car is driving, that's it. And the prime use case of a quantum key distribution platform is distribute keys, that's it. We don't want to have any unnecessary complications by having dependencies towards the key consuming level. Second design guideline is whatever we are doing with the new kid on the block is should be minimally invasive. So there should be no drawback or no impact on existing network assets. And that is what I liked when Matt was talking about things at Verizon. So most of the things should stay as they are, and only when necessary it should be adopted. And especially established protocols that we are using by now, like TCP, IP, all these stuff that is well established and which you cannot change or cannot be changed easily, should not be changed. So that is one of the paradigms. Everything stays as stable as possible. And finally, it's not only the integration into networks, but it's also the integration with what we already have on the security level. So the smooth integration into security environments. Here we have to, and that's mandatory, that's not discussable, we need to have coexistence with what is already existing today. And this applies also to future developments in terms of post-quantum cryptography. Yeah, that's it. Thank you very much for listening.
Oh, Felix, thank you so much, because you are actually addressing so many challenges here. I mean, I can see the quantum decoding, the limited range, the implementation again. So the security assurance, which is one of the main things. So this is really important. And there is something that there is some people that can help you. I know KeyQuant is your partner, as you say. So we have Ulrich Eismann in here. So Ulrich, can you comment a little bit about this?
Of course I can. So hi, and thanks for having me over. Thanks Felix for the talk. It was really interesting to see. Comment of mine would be that yes, it's really challenging not only to build the QKD systems themselves, but also all the key management which goes with it. This was mentioned also in the British Telecom's talk. So that's for us, also from our perspective, really one of the most challenging parts, not only to provide the systems, the QKD systems for the networks, but also the entire management which you need on top, like the additional layers. I think that's really important, and it's stressed, and we work together also with Felix in order to make things happen.
Yeah, thank you. So we know that with Keyquant is one of our members. Could you please? I know you have something to share with us. Could you do that?
Yes, I would. Hold on
This
a
is
second.
the moment.
I guess so. Yeah. So let me see where do we have the sharing button actually? This one, the green one. All right, here we go. All right, can you see the slides or the slide? It's
yes.
only one.
It's only
Excellent.
one.
Excellent. I was asked to bring only one slide. So the question is, how do you compensate a company existing for 2-3 years into a single slide? We tried to do this earlier when we were addressing investors, but probably that's a similar audience which we have here. So the idea of Keyquant is to provide, well, state-of-the-art products, first of all, which you see here. You see, the big clunky 19 inches racks, which will probably work pretty well in the backbone. They have a high price tag. You can manufacture them in small quantities, and manufacturing actually means manufacturing, so with your hand. So they're highly trained people who need to do this themselves. So this is pretty costly and not very scalable in terms of business. And for us, let's say this was not the reason to found the company, but rather to use the continuous variables technology and bring all the functionality which you need from the electro-optics side on a PIC, like on a photonic integrated circuit. And in terms of, in the case of CVQKD, you can actually put the entire functionality, including the detection, on a single chip. So you would have a transceiver chip, very much like it maybe from Coherent Telecom, and rather than providing back and forth 100G, 400G, or even terabit capabilities for classical data, what this chip would provide to you is, well, QKD, so keys out of each side of the communication lines. And once you have that same technology running, you can integrate this into like the standard telecom pluggable modules, CFP, SFP. And that's, of course, we put these numbers like 100K, 10K, and so on in order to shrink this down to a nice marketing message. However, this also stands for things like cost reduction, first of all, naturally, but also producibility, integrability, and finally having something which is scalable in the access networks, as we heard before. Now, let's say from the product side, we're mostly concentrating on the left-hand side for now, because there are these nice European projects, which we have heard about from Felix, for instance. However, on the R&D side of things, we have the first PICs running in the lab. So there is light out of the PIC, there is light coupled into a fiber. So this important interface is also taken care of. And I think along the lines of our future developments, we will have also the right-hand side products in a few years. This being said, I addressed this before, we also work on key management systems. So that's also something you need to care about. And maybe an important factor for the people from the Euro QCI domain, Keyquant is 100% EU27 funded, both for the private equity as well as for the public funded projects. So, well, thanks, and I'm open to questions.
No, excellent. Because actually, this is a significantly reducing cost, which is, is one of the challenges here, because all this technology is so expensive, but also helping with the implementation, because if it's a pluggable, is going, as Felix says, is you want to disturb the less possible on the structure that you have, so the deployment is not going to be that much difficult. And one of the things that Felix was talking about also was that for the Demo Quant program, this is like right now we don't have the proper standards. So Germany is doing their network, UK is doing their network, different countries, France is doing their network, every different country is doing their network. And I think this is the moment to everybody to talk together and get the standards, because everything is going forward, and it seems to be happening soon for different purposes, not for the everyday. It's not I'm going to have a quantum communication here in my home, but it seems that it's going to be start coming soon for big enterprises, for banks, for security, for defense, and all this kind of things. So I think this is like, I mean, Felix, this is really good, and also Ulman. There is some a couple of people that can help you here, Felix, and we are talking about quantum memory. So we have two of our members, and I will call both of them. So one is Eleni Diamanti for Wecklin and Noel Godard for QNet. So Eleni, could you please open your mic and comment something about that?
Yes, hello.
Hi, thank you coming. Thank you.
Nice to see everyone. Nice to see everyone. So I'm here as representing Willing and also as a QKD academic researcher. So it's very nice to see everything that is happening in this field. So yeah, I mean, a lot of the things that have been shared by our colleagues from the telecom operators, so Verizon, DT, BT, are obviously very relevant for all the technologies that are being represented here. So beyond, of course, the QKD systems that we have been looking at, we need to start considering as well long links, and this is where quantum memories can play an important role as well in the future, in the next stages of the quantum networks. So yeah, so I don't know if you want me to also give the short.
Oh, sorry, yeah, sorry, Eleni. Sorry, could you please stop sharing the? Yeah, Ulrich.
Yeah, I can.
Yeah, sorry. Yes, thank you. No, yeah, sorry, Eleni, sorry I interrupt you. And actually, if you can share yours now, yes, thank you.
Is it okay? Can you see?
Yes,
Can you see the slide?
I can see the slide. Yes.
Okay, so I'll go fast. I know there is like not much time in a lot of people. So WeLink is a newcomer in the field of quantum communication. It exists for 1 year now. So the overarching goal is to provide links for future quantum networks by interconnecting quantum processors to increase, of course, their computational power and be relevant for multi-modular architectures of quantum computing, but also make them accessible at a distance via quantum channels. So the entire vision is to develop a full stack, both hardware and software solution that can be ready for deployment in quantum communication and quantum computing, high performance computing, integrating quantum computing infrastructure. So you see here the main idea. So the idea behind using a quantum memory for such links is, of course, that this allows synchronization of the arrival time of the photons. And so this enables the efficient generation of an entanglement link that can then, by teleportation and swapping techniques, you can further push quantum information over the network. And then on top of this, you need, of course, to supervise and control the quantum link and apply all the application layer that can go from tasks, application, quantum networking, going from QKD, of course, and long distance links based on quantum repeaters, this type of technologies, quantum memory based technologies, and beyond, and applications that go beyond QKD. So the vision of the roadmap of WeLink is based on a neutral atom technology for this quantum memory. It has shown record high efficiency for approaching 90% for storage and retrieval efficiency. And so this is a key parameter for enabling this efficient synchronization in networks that we just saw. And so the first product is planned in the roadmap to be available, commercial product within 2 years, industrial grade product. Yeah, so this concludes the short presentation on my side.
Thank you so much. Yeah. So this is one of the big challenges also, like how to do the quantum memory, because I mean you have like little bits in between, so you can create, you can transport, you can deliver the data and everything, but how to handle that or how to accumulate.
Essentially, entanglement distribution without storage is inefficient, right? Because you have probabilistic processes that are happening that are not inherently synchronized, and so by including these techniques, essentially you make your entanglement distribution efficient. So you have available as a resource, this important resource for quantum networking.
Exactly. That's part of all this key. So this little piece. Thank you so much, Eleni. And we also have Noel Godard from Connect. So Noel, are you around? Because you also have some memory quantum memories.
Yes. Is it possible to also share my screen?
Thank you. Hello.
Hello.
Welcome.
Thank you.
Yeah.
So thank you for the invitation to also join today. Hopefully I'm also, I see I'm having the same problem. Can you see my slide?
Now I can see it. Yes. Okay, perfect. Yeah.
So similar to Eleni, I think, both WeLink and QNect represent what we like to think of as like a second generation quantum communications technology. So what we've heard a lot about today is the fact that QKD, which is now going to be certainly pushed to new limits in Europe, largely through the Euro QCI initiative, is an important first step in starting to establish secure communications between users. And what's very exciting is that QKD has the sort of backing in the European community that has not really been the case in the United States, so that you're actually starting at this point to see use cases. And what all of the telecom providers have spoken about today is a big challenge for all of us in both the quantum networking side and the quantum communication side. And that's thinking about how does this stuff get deployed in the real world? And that's truly the mission of QNect. So QNect started by, again, being focused on quantum memory technologies, which has always been thought of as the sort of missing link in being able to support entanglement swapping protocols, which is really the lead candidate for being able to do distribution of entanglement at long distances. So similar to WeLink, we also work with atomic vapors, but we work with atomic vapors which are actually at room temperature. And it turns out that there are numerous processes which can be used for doing quantum memories at this point, but the process which we use is called electromagnetically induced transparency, which allows us to be actually able to turn the memory on and off by demand. And we introduced this instrument into the market, which you see on the upper right, the quantum memory in September of 2021. It is geared to actually store one photon at a time at 795 nanometers. So that's near IR. It's ground state of rubidium. So that is not telecom. And that's one of those big problems that sits out there whenever we start thinking about how do you get quantum into the real world. So I've listed here on several bullet points a lot of the things which guide the design principles at QNect and why we started to think about how we design a full product suite. And in fact, 4 of the products which you see there are already in prototype mode, and we've sold several of them to researchers who are already using them in the community. So we build an entanglement source that's labeled QSource there that actually acts as the sort of patch between the quantum memory, which is not operated at telecom, and the telecom world. So our suite of products, which supports entanglement swapping, is a drop-in solution to actually operating on existing fiber networks. We operate in the O-band, and I think there's some advantages to thinking about how quantum is going to coexist with the existing classical communication which is out there. It's very easily filtered from the rest of telecom, which provides a lot of advantages if you're going to have them in the same fiber cables. We require, in our case, no specialty cooling or vacuum infrastructure, which we think is very important for being able to facilitate scaling. When you start talking about needing to put things every 25 to 50 kilometers along a network, it has to be something that is not supported by a collection of instruments, which is cost prohibitive or, energy prohibitive. We also spend a lot of time thinking about how to make our designs stable with very minimal maintenance. I think all of us face the same challenges in quantum communications, quantum anything, is that the degree of precision which is needed in order to do the stuff that we'd like to do, like these transactions at the quantum level, very often put us in a regime where all the instruments are highly sensitive and need tuning, continuous tuning. So we spend a lot of time thinking and engineering about that, and that certainly plays into the last speaker who was talking about the PIC systems. I think that's where we all hope our community will start pushing towards. That way we have things which look very much like the classical components.
Thank you. Thank you so much, Noel. I mean, this is really good. So we need to move forward a little bit because we really have to keep the time. We say 2 hours, and it have to be 2 hours. After the meeting, we can stay talking about. We usually keep the room open, but for the broadcasting, so we continue. So the next speaker is going to be Hans Brunner. So Hans is coming from Hawaii. Okay, and he's an expert in quantum cryptography, in Raman spectra, optical noise, quantum optics. He's in the wavelength division multiplexing. So we really have a very good representation here. So now we are moving for who are going to be the providers of the telecommunications. Hans?
Yes. Hi, can you hear me?
Yes, so the floor is yours. Thank you so much.
Thank you very much.
Yeah.
Yes, very glad to hear you. To be here. So thanks for the invitation. I'm gonna share and try to. Always that. Am I now sharing the full view?
Yes, we can see you perfectly. Crystal clear here.
Okay, well, I will talk about our QKD solution that we have built as the Munich Research Center of Huawei. And my very first slide, I assume you all know this inequality, so I don't want to actually introduce it too much. But to address Andrew's statement in the very beginning, where he was saying that still the customers are so reluctant in going in this direction of using post-quantum security, QKD, and means to be secure, also future-proofly secure. And Moscow's inequality says that if you want, the issue is as soon as the quantum computer is here, it will be able to decrypt everything which we have encrypted in the past. So if you want to have some data which is secure for at least D years, you should start implementing quantum cryptography at least D years before the quantum computer is available. Even more problematic, it will take you time to implement quantum cryptography. But this is not what I wanted to address. What I wanted to address is it might lead you to it might be insufficient when you start interpreting it, because when you think of it, when is the cryptographically relevant quantum computer available? Usually is interpreted as, okay, the universal gated quantum computer with roughly 1,000 noise compensated qubits. This is not available yet. People start claiming that the quantum supremacy is achieved, but we're not there with 1,000 qubits, so we still feel kind of safe. And we here all wait for the point where people start jumping on QKD because suddenly the quantum computer is there and everybody's threatened. But I think, so it just leads you to statements or risk assessment like saying, okay, the probability of a cryptographically relevant quantum computer being available in 10 years from now is non-zero, which is a conservative and stable assessment. But I want to say 3 things which might challenge this view. First is a universal gated quantum computer and a device which breaks RSA is not necessarily the same. The universal gated quantum computer is sufficient, but it might be not necessary, right? There might be something easier. The Turing bombs used in the Second World War broke the Enigma without being universal computers. So it's a very specific, specialized device. The second point is research on breaking RSA is highly regulated. Even in Germany, if you would do it, you would even break the law, or possibly break the law. So it is actually a military application. While implementing cryptography is a dual use or something we want to do, but breaking encryption is definitely application more in the military domain, therefore more in the you want to keep it secret. And the third point I want to say is, imagine the worth of being able to break RSA without anyone knowing, right? It's like the zero-day exploit of all communication. And until nobody knows, it is extremely valuable. Also, the being able to break Enigma was kept secret for decades. So summing this up, I would say the probability that there is a cryptographically relevant quantum computer already available for 10 years is also non-zero. But this was only maybe a bit too much in the conspiracy theories, but I see it actually as quite realistic. So what have we done? We have also, as LuxQuanta and KeyQuant, built continuous variable key distribution. Our design criteria was to keep it as simple as possible and push as much of the complexity into the digital domain, which makes it quite flexible. You can change the protocol at any time. And also from the security point of view, you can analyze it more easily because you have less analog components. So there are less nonlinear behaviors. And also the code you have doesn't really age. And also it allows a very flexible configuration, which is also already addressed by the telecom providers. The device, or as a very valued colleague of mine used to say, the engineers, or I'm paraphrasing, but the engineer's fallacy is to believe that whatever he's doing is the center of the world. But QKD is just a key exchange. So it cannot be that everything has to be built around it. It's just a key exchange and it has to adapt to what is there. So this was one of our design criteria to make it easy and very easily integratable into existing networks. On the right-hand side, top graph, it's a block diagram of what we have in our box, and it's really straightforward. It's a laser, it gets modulated, attenuated. Most of the power is observed so that we can show or observe or transmit power. Then we go to the receiver, and it's not a standard coherent receiver, but very similar to a standard coherent receiver. So all of this is knowledge taken from communications. It definitely is a low-cost implementation. It's built from readily available components. There's nothing special. It has no special temperature requirements. And as others already have talked about, it can be integrated photonically quite easily. Below, you see actual pictures of what's inside of our boxes, and the optics are really simple and exactly the block diagrams you see above. On the left-hand side, you can see a graph of our reach, and the red dots are actually end-to-end measurements of key rates, which we really ship to key managers. So it's a quite advanced prototype. We are not building product. For most distances, or up to 50 kilometers, we can give out 10 kilobits per second. But we can also push it. Someone before said it in the deluxe version of what was it? In the, up to 23 dBs of loss, which is in this plot 110 kilometers. No, that was 22. On the right-hand side, you can see of these plots, you can see the co-propagation performance. So an inherent advantage of CVQKD that it's more robust to wideband noise like Raman scattering, and therefore it can more easily be co-propagate with classical communication. For example, here at 30 kilometers, with our system, you can have up to somewhere between 25 and 30 co-propagating classical channels, of course, depending on their launch power. We have tested this in the Madrid quantum testbed, which is a quite large and advanced quantum testbed. We have brought 10 devices, 5 transmitters and 5 receivers. And in this testbed, we have demonstrated quite a few features would say, advanced features of QKD devices for especially targeting on network integrations. So, for example, on this link on the top left, Piron to Quixote, I'm not very firm in Spanish. There was already, this is an operational environment in the Ready Madrid network. Ready Madrid is a telecom provider for the research network in Madrid. So it connects universities. And in this link is actually in use, and there was already OTN equipment deployed, but it had a few free multiplexer slots. And our devices are built in such a way that you really can just go there, plug it in, and it will work. So we call this a zero-touch integration because it won't disturb anything. You don't even need a downtime of the communication, which is already there. Also, it only needs one lambda for everything, but you need another reconciliation channel, which is not necessarily optical. It can go over the internet. Our devices are fully tunable in the C-band, while the setup here has limited to 2 DWDM channels, channel 37 and 38. And it is built in such a way that actually any transmitter can talk with any receiver. So it is like a switched network with, if you want, ROADMs. So with these 5 transmitters and 5 receivers, we were able to build, and with the 2 different lambdas, we were able to build not only 5 links, but actually 35 different links because of the switching, the optical switching capabilities. Which is also in linear networks a real cost advantage, right? Because you don't need to have a sender, a receiver at every single node. You only need a sender, a receiver, a sender, and a receiver. So you cut the cost by 2. Yes, and we also integrated this with the key managers are provided by the Polytechnical University of Madrid. We haven't developed our own. We're just integrating it there, and they then give the keys to the actual applications. It was tested with several different encryptors. This is a zoom into the switching capabilities. So everything is dropped, but the QKD devices. So every orange box is a sender, every green box is a receiver. In between, you have the blue boxes, which are the switches, and the multiplexers. The blue boxes and the multiplexers together are like the ROADM. And on the right, you see several possible configurations of how it could be switched to show that really everybody could talk to everyone. But some of the links have too much loss, and therefore they're not possible, but most links are possible. So to conclude, I believe we have a very thoroughly investigated and robust QKD implementation as prototypes. It is software-defined for maximal flexibility and central configuration together with UPN. There is also developed an SDN control interface with netconf and zeroconf and all this. This is not my domain. I can just refer you to them. In order to control the devices, and you really just dump them, say you talk to them, you sender talk to this receiver switch, and that's it. It's as CVQKD is, it is a low-cost implementation with a clear road for full integration in high volume. I wouldn't even say that having QKD at every home is impossible. It's definitely possible to scale this down to extremely cheap implementations. Only the computational complexity is still a challenge. So the reach and the key rate are definitely optimal more for metro environments rather than for long distance. And it also has this high tolerance to co-propagation, so it's ideal for all these setups which were already addressed in this session here. There is this possibility of the zero-touch integration. So if you already have some OTN, some customer which has one or a fiber, we always tried it with a fiber pair, but we also could have tried it with a single fiber. If this is already there and you have a few slots empty on your DWDM or CWDM multiplexers, just plug it in and it will work. It was demonstrated in the field, so the TRL level is quite high. And with this any-to-any connectivity, we can have a network of N nodes with only N devices, which makes it much cheaper than having a node pair for every link. So it's definitely scalable towards simpler and cheaper and smaller implementation. Thank you.
Thank you, Hans. That was great. Do we have any questions out there from our community? And I think Elise or Helena will help me if we see any hands up. Okay.
Sure. Sorry, I was mute again. So sorry. Thank you so much, Hans. So it's amazing to see that that this is possible. I mean, really. One of the things is, okay, this is prototyping stage. So what is your projection for for moving forward to when do you think we can see a product?
Well, I have to disappoint you in this respect.
Yeah.
I'm in the research group and I have literally no ties to the product line at all.
Yeah.
So I cannot comment at all. I don't know.
Okay. Okay, you don't know. Yeah, it's just because it seems. I mean, it is nice to have a prototype that works, but still, to see the link in between that and the product, I don't see it like very close yet. So yeah. So anyway, so thank you so much. Yeah, one of the things is the scalable. I mean, I come from production world and I know how scalability could be so much difficult. It's not straightforward. Do we have
Helena, do we want to invite Quaint LR to do one quick is Quaint LR out there? Why don't we have them? And just why don't we do this? We're going to have Quaint LR present their one slide. Let's try to stick to 1 minute, and then we'll go through our next two speakers, and then we can do any slides at the end. So
perfect. So Janir Favea, are you around, please?
And Hans, yeah, there we go.
So for Quant LR, it's Nitzan, it's not Yanir.
Oh, okay, sorry.
Actually, it was supposed to be Yanir. Anyhow, you got me. That's
That's
good to do.
But it's nice to see you, Nitzan. Yeah.
So unfortunately, it's not one slide. I guess we missed a bit the format, but let me just go quickly through it. So, well, I'm the CTO of Quantelar, and well, thanks for giving us the opportunity to present the company and our vision. So, can you see? Oh, okay. So, well, I guess you've seen a few of these images in the past. So in the last few decades, QKD made its way from theory and research lab to the academy and to the industry. And the market is now coming of age. So different use cases are being explored by the data center giants, by critical infrastructure, by financial institutions, and especially, well, as we've heard, by telcos that are looking to deploy countrywide QKD backbone to be used by different government organizations at the first step, and later by any entity with sensitive information. And plans for mass deployment of QKD networks are actively being worked on. So the majority of the industry is focused on single link point-to-point solutions, and innovative firms have focused on developing different protocols, increasing the secure bit rate and extending the operation range of QKD systems. And this helped to move the industry from just a promising technology to performing field POCs of real use cases with real clients. But current solutions are seriously unprepared for the real-world QKD networks, because single link solutions can only go so far. And for a digital world, utterly dependent on global interconnectivity, well, secure communication between any two parties is a must.
Sorry, yeah. So Nitzan, sorry. So we asked for one slide because we actually have to follow the program. So what about if you tell me? What about if you tell me what is your major challenge and what do you need? How others can help you?
So well, how others can help us? Well,
yeah.
So in Quantelar, we develop well, different QKD solutions for the different network segments.
Yeah.
So one thing that we could,
or you can help others, true. Yeah.
Well, first of all, I hope that we can help others, especially when it comes to deploying a large number of QKD links and in a dense urban area with multiplexing of the signal onto a single optical fiber. And I guess that we could also get some help from the industry for moving forward from, well, off-the-shelf components, yet discrete components, to integrate the optics, especially for the transmitter. We have a unique design for the transmitter well, it's BB84 decoy state, yet a unique design, and we are looking for partners to help us move forward to integrated photonics.
Perfect. Well, thank you, Nitsan. I really appreciate that. And again, we're all here together. How can you help each other? How can we help you? How can we help Nitsan? So thank you so much. And maybe stop sharing your slide because we'll have our next speaker come up. We're going to welcome Alberto. So Alberto Coman, he is the leading R&D projects manager in quantum communication at Airbus. It's such a pleasure to have you today. Airbus is leveraging the quantum technologies to improve performance to help solve the aerospace industry's most complex challenges. And I believe we have probably the leader in the field to explain it to us. So thank you so much, Alberto. The stage is yours. The slides there. I can't hear you. Yeah, I cannot hear you, Alberto, so I'm not sure. I hope you're back there. Okay, so Alberto is there, but we don't have sound. So my apologies. I see his arrow moving. So if I had.
Okay. Hello, everyone.
Hello, perfect. Hello.
Here you are. Yay.
Hello, that's yeah, it was muted. Sorry for that. So this is Alberto Comin from the Airbus Central Research and Technology in here in Munich. In Airbus, we have a strong interest for all quantum technologies. For example, quantum computing or quantum sensing, or also quantum communication. And in quantum communications, we are participating to the future European quantum communication infrastructure, the so-called EuroQCI. This is a major European initiative which involves all the 27 member states. Within this context, Airbus has led several design studies in the last few years, and some of them are shown here on the right-hand side of this slide. You can see, for example, the project COSAC and Octavo, which were mentioned before in the previous presentations. As you know, the EuroQCI will have both a ground segment and also a space segment, which is developed under the ESA program called SAGA. And Airbus is active in both the ground and in the space segments. In the ground, we are preparing to participate to the overall network deployment. On the space segment, we are active at both the European level, in the project SAGA, and at the national levels, for example, in the French QCI or German QCI. Airbus is developing some of the key building blocks, which will enable future space-based quantum key distribution. We are preparing solutions for both prepare and measurement and entanglement-based quantum key distribution. Some of the key building blocks are shown here on this slide. For example, we are developing telescopes compatible with QKD. We are developing quantum key distribution satellite payloads and also ground stations. To conclude this speech, Airbus is very active in the development of the future European quantum communication infrastructure. We are participating at both the overall network deployment and also we are building some of the key building blocks of the future QKD. And with this, I conclude and I leave the floor for questions.
Wow, that was a very, you did very well in timing there. So thank you very much for that.
Yeah, thank you very much. So you say that you are planning for doing the deployment. So
well, what I'm referring to is by deployment is that we are participating in the project Petrus, which was named before in the Deutsche Telekom. That's about the deployment of the European QCI.
Okay. Yeah. So you are part of it. Yes. Okay.
Yes. Yeah. That's what I meant. And on the space segments, we are also involved into the single component like the telescope or the payloads.
Yeah. So we have one question for Konstantin and Nessie. Konstantin, could you please tell yourself your question?
Yes, sure. Hi,
Thank
Alberto.
you.
I just wanted to ask if we have an estimate of the number of satellites that you think will be necessary for these European constellations being developed in EuroQCI. And also, for a later question, do you have apart from obviously what you're developing regarding the telescope, do you have other critical components that you see that will require development by either you or other companies to provide a successful QKD service via satellite?
Okay. Yeah. Thanks, Costantino, for the question. The number of required satellites. It's a question which has been maybe asked and replied several times. To be honest, I don't have my own answer. I think it really depends on the use case. But yeah, I think it depends on the use case. I mean, I don't have a more specific answer rather than what emerged from the COSAC studies. Regarding the key technologies, I think we still need to do some development on the sources to make it more standardized, more streamlined. Now we have several companies such as yours, which have excellent products. We do have products in, say, QKD sources, in quantum number generators, also in the surrounding ecosystems. But as you know, the big challenge is to make these sources, say, and this technology hardened, to make them certified and usable in practice. This, I think, will be the challenge. This will be on the ground and even more so in the space. I think that's my take on it. We can discuss later offline if you want.
Absolutely.
Thank you. Thank you so much. So since we are tight for time here, I'd like to introduce our next speaker. And then I'd like everybody to stay around until afterwards. We can all stay as a group and ask some questions and be together. Right now, I'd like to ask Helmut Krischer to join us here. He's Director of the Advanced Technologies at ADVA Optical Networking and a great contributor to this event. And I'd like to thank him for joining us today. So do we have you here, Helmut? So he'll be joining us in just a second.
Yeah.
So
yeah, I'm here.
hi. He's joining us. Thank you for the patience as we get switched over here in the last little bit. And if there's any of the questions outstanding, yeah, if you'd like to stay around afterwards, we can do that. And Carl will have some good questions for us as well. Right, Carl? Okay, thank you.
Can you hear me?
Yes, we can hear you.
Okay, then, and I guess you can see my slides as well.
That's perfect. Go ahead.
Okay, thank you very much. Thank you for inviting me. I wanted to give a view on the state of quantum key distribution from a network vendor perspective. So we are working with QKD devices already since 6 years or even more. And we are looking, or we did very closely look at how to integrate QKD into networks. And if you talk about quantum key distribution and try to get an overview, so you see that there is not just one quantum key distribution, there are many. And for the question for integrating is now what are the better options? So I don't want to go into that detail, and this is certainly a very rough and subjective classification, and I'm quite sure that everybody of you will have a slightly different view, but I think it's clear that we do have many options for QKD, and it's not quite clear what is the best option. So we think that in general for systems, also looking into networks spanning from the core nationwide networks to the access, you should be agnostic to specific QKD technologies and be able to mix and match those different technologies and implementations as it might fit, and also give you a cost advantage. With respect to cost, you might have seen that I didn't put any cost estimation here, because I think what really matters is how the cost will scale with volume. I think what we see at the moment are devices which are more or less very small series or single devices, and the question is, if you compare it with transceivers, optical transceivers, how cost will scale. If you look at the performance, I think this graph from a paper from Luca Marini gives a very nice overview of where we stand with respect to the key rate versus attenuation. Here an attenuation of 0.2 dB is assumed. So you can see that you basically have a range of experiments for discrete variable QKD and also continuous variable QKD, and you're limited with respect to the distance. In practice, the distance is very often shorter because you have higher attenuations along your line. But what we can see very nicely in the picture is that it's actually you have certain bounds, and you would need a quantum repeater to go beyond this bound. There is only one exception, which is actually an interesting development. This is this twin field QKD, which actually can cross the bound for the repeaterless bound. On the other hand, if you look at the area where you really have a gain from twin field QKD, I think at the moment it's not quite clear if you will gain something. But in practice, we are limited very often to distances which are below or even far below 100 kilometers. If you now look at the status in standardization, then there is the ETSI QKD group, which did some very early and fundamental work for QKD standards, so especially with respect to interfaces. And they also looked into common criteria protection profile, which is, I think, very important if you think about certification. There are other standard bodies, for example, ITU, who in a top-down approach issued already quite a lot of standards for QKD networks. Activities are also happening at IZO, where they made up a framework for QKD evaluation, which, according to common criteria, which would be important if you think of certification. And more recently, CENELEC also started a focus group and looking into the standardization roadmap. So what I wanted to emphasize here is that standardization is really important, not just for the interface, for interoperability, not on the quantum channel, obviously, but on the digital interfaces. But it can be also an important first step for certification. So this is my last slide. So if we think about integration of QKD in the optical networks, the pro point is that we already have a fiber network that also can transport the quantum signal, but this usually comes at an significant cost. So you either need an extra fiber, or you might need to go into the O-band, which reduces distance, and you have additional security requirements for the trusted nodes. If we look at integration option, so for long distances, it's certainly advisable to go with dark fiber and to use high loss margin QKD to minimize the number of trusted nodes. Where for short distances, especially access co-propagation on a single fiber scheme with few wavelengths might be an interesting option. We still don't have very good models for planning and leveling if you do co-propagation, and obviously, which was mentioned before by other speakers, authentication and the management of the QKD network is required. So from our point of view, QKD will be on for classical and post-quantum key exchange. It comes with an extra cost, but it's the only solution that can provide long-term security. And certification and standardization for QKD devices is a must to have really a broader market. So if we don't have this, the market will probably be small and not really leading to cost reductions. So to end with some positive message, so actually we are supporting using quantum keys for commercial encryptors, and so we have those encryptors available to use together with QKD systems. Thank you.
Thank you, Helmut. Thank you so much for that additional.
So
Yeah,
we need to close for the YouTube. So we continue doing this. We continue in the room, and everybody is going to have. We are going to mail the slides. Thank you so much. Thank you for all our speakers, to our Optica team, to Carl Williams for all the support, for all your participation. Okay, I'm very happy that we have been addressed for all these challenges that we were talking. So quantum decoherence, limited range, complex in the implementation, the security assurance like this.